We are looking at example 6 on page 91 of the workbook. And this is giving us a series and asking us to determine whether or not it converges. Okay, so at this point in the course, what we have are two possible ways to test whether a series converges or not. We have the divergence test, which we talked about earlier, and the integral test, which we talked about more recently. Okay, and at the outset, I don't know which test is going to work for us. So let's do a little bit of scratch work here. Think of this as just a process. We're going to experiment a little bit and see if we can figure out which test might work for us. All right, so I'm going to start by trying the test for divergence, since that's usually an easier test to apply. That's the one that just says we're going to take the limit as n goes to infinity of the nth term in our series. And notice that if we take that limit, we're going to have to get 0 because the denominator, n ln of n, goes off to infinity, which is going to make the whole fraction go to 0. Okay, now the question is, what does that calculation tell us? Okay, well, if you look back at the divergence test and what we said about it, there was a caution below it that said that if you take this limit and you get 0, unfortunately, the test doesn't give us any information. It's inconclusive. Okay, so the divergence test doesn't yield any information for us. What does that mean exactly? Well, it just means that we need to try a different test in order to determine whether our series converges or not. And so we move on to the only other test that we have at this point, and that's the integral test. All right, so we're going to take the integral of the function 1 over x ln of x. Looks the same as the term in our series, just that we're thinking of it as a function now. Okay, and doing this integral involves setting this up as a limit. Okay, remember, notation is important here, remembering to write that limit sign. Okay, and as you look at this integral, you might notice that a u substitution looks like the way to go here. Okay, I'm not going to write all of the details of the u substitution, but you can kind of check this on your own. If you let u be ln of x, du is going to be 1 over x dx. Okay, and if you carry through the details of the u substitution, okay, I'm gonna skip that here. Here's what you would get after you take your antiderivative. Okay, and finish the u substitution process. You're going to get an antiderivative that looks like ln of ln of x. Okay, and that's going to get evaluated between b and 2. Okay, and continuing here, next step would be to plug in our limits. So the upper limit is b, so we're going to get ln of the absolute value of ln of b minus the lower limit, which is ln of the absolute value of ln of 2. Okay, and the question is, what happens as b goes to infinity? Okay, well, we've been in this situation a few times before, and we made the observation that as b goes off to infinity, ln of b is also going to go off to infinity, which means that this limit that we're taking is going to have to be infinite. Okay, so what is all of that saying? Well, what we've just discovered is that this improper integral diverges because of the fact that we got infinity instead of getting a finite number. Okay, so the integral test then just says, the integral test says that because this improper integral diverges, the series that we started with at the beginning of the problem, that must also diverge. All right, and so to finish, we just need to write our proof. Okay, we've completed our scratch work. We've successfully used the integral test. Here comes our proof that our series diverges. Okay, so since we calculated that integral and we got infinity, that integral diverges. We know that the series that we started with also diverges. Okay, by the integral test. Okay, and just to emphasize again, okay, problems where you're talking about series convergence, it's important to write that proof